Hi everyone. Thank you for signing up for this. This style of, I guess, more of a lecture style is more what I'm used to, and I haven't quite figured out how quickly I need to speak and how much I need to put in. So I'm not sure this will last a full hour, but I will do my best. And if it doesn't, then I'll upload another video or an extra video afterwards. This is our first one we've done. Got the organic chemistry one as well, but that kind of relies on the knowledge of this one. So, it's lecture style recordings for roughly an hour. Sometimes I talk too fast, sometimes I think I can get through more than I do. And I'll also be doing a 2-minute and a 5-minute video explaining a concept based around tutorial questions. So they will be emailed out after the seminar. Normally, they'll get emailed out straight away, but I'm not sure this week. They'll be out sometime within the next day or so. So week 1 is maths for science. The most common thing, and this will be by no means comprehensive, but the most common things I see students struggling with. And I've picked a couple of them. A couple of the main ones that I've seen people struggling with that seem to get tripped up once you get into grade 11 and 12 and into university as well. The grade 11-12 curriculum mirrors the university curriculum. The university curriculum is ever so slightly more complex in the way that it's taught. So it's being recorded. I won't really have a chance to answer questions during. I may cut them to 50 minutes or 45 minutes, and then we can have a Q&A at the end for those that do attend. So I'll upload the recording straight after the session. So as soon as it's done, I'm going to create a playlist on YouTube and I'll be uploading it to there. And I'll post a tutorial question as soon as I can. So, why maths? I think once students get into year 12 and get to the pointy end, that's where they fault. Some people are naturally good at maths. A lot of people aren't, including me. I was never good at maths. I had to really dig deep just to even get through the basics, and I really struggled when I got into uni. So hopefully you can learn from my mistakes. So, scientific notation. I'm going to use the whiteboard a fair bit in this one. So Avogadro's number is 6.022 times 10 to the power of 23. Which means that there are 22 zeros after the decimal point. So we can't really present that kind of number without doing this. And part of the reason we do it, and part of the reason we use significant figures, which is next, is to reduce the risk of a mistake being made. If you only have to write out 6.022 times 10 to the power of 23, then you don't risk missing a zero or adding a zero. So we know in science and in chemistry, we have to be very, very specific. So there's a few other ones there. 2.103 is 2,130. Sorry, 2,130 is 2.13 times 10 to the power of 3. 7.5, sorry, the other way, 0.00075 is 7.5 times 10 to the power of minus 4. So, when we're talking negative numbers, we move the decimal point to the left. When we're talking positive numbers, or sorry, positive to the power of, we move it to the right. So if we were to do, whiteboard out now that everyone can actually see it. Do this practically, and it seems really basic, but it is one of the first things that they'll teach you when you get to year 11 and 12 and uni. So 2,130. And I'll tie this in with significant figures next. And in hindsight, I should have done this significant figures first. But so 2.13 times 10 to the power of, sorry, seeing this number, there will be 3 numbers beyond the decimal point to the right. If we were to go the other way, and we were to do, so 0.00075. So there are a number of reasons why we might not be able to use this number in a calculation. So we want to represent it in the simplest way possible. So we need to get to a whole number, or not whole number, a number 7.5 and no longer a 0 point. And this will make sense when we get to significant figure. So we need to reduce this to here. So we would do it would then become 7.5 times 10 to the power of -4. If we want to go backwards, if we would, you might get a question in an exam that says, shrink this into scientific notation. This is what this is all about, scientific notation. When you get into complicated stuff like stoichiometry, there's some more complex maths, enthalpy changes and things like that. If you don't get this right, then you've lost yourself half a mark already, straight off the bat. So it's really important to get this stuff right. So, -4, we move this 1, 2, 3, 4. So it would be 0.00075. To go the other way. So let's say to go negative. If it says 10, if it says to the minus of a number, you immediately bring this back to here. If it's a positive number, you go to the right, or you're adding zeros, so you go to the right. Negative number, taking zeros away, you go to the right. So, really not very exciting concept there, but an important one nonetheless. So, next one, which is not even slightly more exciting, is significant figures. Significant figures are important because when we are talking here, we're talking about uncertainty. And the classic one is millimeters. 21.2 millimeters has a lot more uncertainty in that number than 21 millimeters. So if we go back to scientific notation, we have to use the part of the equation that has the smallest number of significant figures. So if something has two significant figures and you have a number like this, or say three significant figures, and you have a number like this, then you have to represent it as standard notation, a scientific notation. So we have rules, like everything in chemistry, and most things I teach, there's exceptions to the rule. For significant figures, there's not. It's pretty standard. So all non-zero digits are significant. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And exact numbers, so 21.2 has 3 significant figures, but the uncertainty is really high. Whereas 21 millimeters has no uncertainty. There's no chance, okay, a little bit, there's less chance that I've stuffed up 21 millimeters as opposed to 21.2. So the one where people get tripped up is in the zeros. So if there are, say, 3 numbers like 205, then the 0 in the middle counts as a significant figure. It has to be used in the calculation. So at the end of a number, that includes a decimal point. So 3.00 is 3 significant figures. If you took that decimal point away and you just had 300, it will be 1 significant figure. So any number that starts with 0.0000, then those zeros before the first non-zero digit are not significant. And at the end of a number without a decimal point, so 300 only has 1, 3.00 has 3, 0.300 has 3. So why is this important? When you get into later years, they will trick you as much as they can when it comes to exam questions. With the advent of Google, with the advent of all of these question banks that the universities employ that you can find quite easily, they make the exams harder and harder and harder each year because the answers are easier and easier to find. So usually they'll give you a worded question with 3 different numbers, with 3 different numbers of significant figures. You have to figure out which of those should be the number of significant figures that you use. And in a calculation, you use the least number of significant figures. So if the others have 4 significant figures and one of them has 2, then you have to use 2. And that's where, if we think back to what we just did, the scientific notation, we can use that to reduce the number of significant figures. Yeah. So 205 has 3. There's a 0 between the 2 non-zero digits. 61.09 has 4. 0.500 has 3. 3.00 has 3, we know that. 0.0025 and 1,000 has 1. So again, it's important because of uncertainty. The least amount of uncertainty in a calculation, the more reliable your answer will be. If your experimental design gets you 0.0007648,026 million, then all those numbers on the end, they don't mean a lot. So if you can reduce the level of uncertainty, so round that to 2, maybe 3, then the results you get when you do your calculations will be far more accurate. So rounding 21.2 to 21 takes away most of the uncertainty in the measurement. So the metric system, most of the world, except for the US and Europe, which I guess is a big chunk of the world actually, use these units of measurement. And in science, these are the ones we use. There are a few exceptions and ones we slot in there. Length is in meter, mass is in kilograms. Temperature, so there's a distinction between mass and weight. So mass is the amount of, I don't even know how to explain it the other way, is the amount of stuff inside. It's the total weight of the stuff inside. And it sounds like a silly explanation, but that's basically what it is. Whereas your weight is the force of gravity that's being pushed down on the earth. So time is in seconds. So I'll touch on this later and go through the maths of not using kilograms and why we don't use kilograms and grams to tell the amount of something. Because they are mutually exclusive. The amount, electric current, ampere, luminous intensity, so prefixes for measurements. We use these, the common ones in chemistry are nano. Biology, you also use nano, but you also get micro as well. So nano is 10 to the minus 9. Micro is 10 to the minus 6. Milli is 10 to the minus 3. Right, what's going on in the chart? Let's concentrate on what's being said rather than arguing with each other. We can discuss that at the end. Anything you want to discuss, happy to discuss at the end. Yeah, so they're the prefixes for measurements. So unit conversion, one that gets people. It seems more complex, but it's quite simple. Everything has a conversion, or you can create a conversion factor. So mile to kilometer, 1 mile is 1.609. 1 hour to minute to second. So 1 mile is 1.609 kilometers. So we have 55 miles per hour. What's going on in the chat? It's really distracting. Right, let's stop the chat because it's really distracting. We can talk about it at the end. So 55 miles per hour to kilometers per second. 55 miles an hour divided times by, so we have what we have over the unit of measurement, so 55 miles over an hour times 1.609 over 1 mile gives us 88 kilometers per hour. Because we're cancelling out miles here, think back to your I don't know, grade 6, 7, 8 algebra. I'm not sure. It must be a long time since I was in primary school. But we are cancelling out these units. And all we are then left with is kilometers and hour. So it's an 88 kilometers per hour. 88 kilometers per hour. Sorry, yeah, 88 kilometers per hour times 1 hour over 60 minutes. So we need to get to kilometers per second. So kilometers, second, minutes, and hours cancel each other out. So then we are left with 88 over 60. Oh, there's you, which is 0.024 kilometers per second. And that is a really complex way of looking at it. An easier way is the unit times the conversion factor. So 55 kilometers, or 55 miles times 1.609 equals the amount of kilometers. I won't do the calculation. But you're just plugging in the numbers. So we've gone through that. So, no worries. Okay, so mass, volume, temperature, and density. Mass and weight have very different meaning. The effect of gravity on an object is the mass. Is the weight. And the mass is the amount of stuff or matter in an object. I left out the word weight. My apologies. Volume is the amount of space taken up by matter. So measured in meters cubed. This is one they will trick you with as well. They'll use volume in liters, whereas some calculations require you to know the volume in meters cubed. So we usually use liters. Meters cubed is an old way of looking at things, and the numbers are always usually very small, whereas liters and milliliters are much more usable numbers. So we don't use Celsius or Fahrenheit, except if you're in the United States. We use Kelvin. And this is important. There was I think it was a European Space Agency's rocket that blew up. I don't know whether it was on landing or when it was taking off, but they didn't get the conversions from pounds to kilograms right. The American scientists were still using pounds, foot-pounds of pressure, whereas everyone else was using kilograms, newtons, to measure things. So now, in this day and age, we all science uses the same, and it's very important. So the density is also important as well. So density is the ratio of the mass of a substance relative to the volume occupied. It's calculated by dividing the mass by volume. So it's the measure of density like water. So if water freezes, its density increases. The only thing on the planet that does that. So it's the amount of space it takes up relative to the volume it's occupied in is the density. It's a really weird thing to try and conceptualize. So, everyone's favorite. PV equals nRT, what we call the ideal gas. Now don't worry about what the actual gas law means and what this all means. It's just something I've noticed that almost all students struggle with, is rearranging the equations. Good at maths, but actually chopping and changing and dividing by this side to get this side is something that students typically struggle with when they get into first year and into to the later years in chemistry and biology, not just chemistry. So trusty whiteboard back out. So PV we can solve for any of these by simply rearranging the equation. So pressure, P, volume, V, and equals the ideal gas constant. Oh, never mind. N equals the number of moles. And R is the ideal gas constant. That doesn't change. It's one thing we don't need to solve for. And T equals temperature. So, very little to do with maths until you actually plug the numbers in. But, so P equals pressure, T equals temperature, N is number of moles, V is volume, R is the ideal gas constant, or 0.0821. So we can solve for any of these using this equation ever so slightly rearranged. Oh. So we want to get pressure. So pressure equals so if we think back to our ideal gas equation, PV equals NT. What we need to do is get rid of V here. So P times V. If we divide this side by V, and we have this here, we can cancel out V on this side by dividing for V on this side. So we need to get rid of the V that's here. We then divide it, the entire equation by V, and we get P equals nRT divided by V. So you'll get a question in an exam or an assignment, what is the pressure? And you immediately know, okay, I need to get rid of V. So I divide V by both sides, and I get rid of it. This simple concept follows through your whole. Sorry, I get in trouble for speaking too fast and going too quickly, so I give people a chance to write stuff down. Hate for Madison to get me in trouble again. So now we can solve for, let's see my mouth, N, using the same method. Bit trickier with N. So the original equation, don't know why I rubbed that off. So I need, because it's N times R, I have to divide it, both sides, by PV. So what happens here is N is transplanted here. We divide. So N becomes NE. So to get rid of this over here, we divide both sides. and then we divide both sides by n, and it gives us n equals RT, PV over RT. Dividing by PV. This is probably the most maths heavy we'll get this whole time, so don't stress. So again, solve for V. This is being recorded, so if I do go too quickly, you can watch it again. So V equals probably it's the simpler one. We've divided both sides by P. So to get the volume, nRT, we've divided this side by P. We divide this side by P to get rid of the P that's here. I don't think I'm going to go through all that. T equals PV over NR. So you're dividing both sides by PV to get T. So you're just following the same principle through. And I'm not going to keep going through all these because you guys get the point. So, commutative law. Think back to like grade 7, maybe grade 8, maybe grade 6 algebra. So it doesn't matter which way we calculate and we add things. 5 times 7 is the same as 7 times 5. And 7 plus 5 is the same as 5 plus 7. But that does not work for multiplication and division. If you have multiplication and division and you do rearrange it, then you will affect the answer. So it only works for multiplication and division. So we know now, we read through these laws, that we can change the equation. Subtraction and division, sorry. Okay. Talking for the whole day talk. So, associative law allows us to arrange numbers in the most convenient way using the same principles that we just went through. So 3 plus 2 plus 5 in brackets, it's the same as 3 plus 2 plus 5. We get the same answer. But we can arrange the equations in a way that's most convenient for us, or like with the ideal gas law, we can find the answer or the amount or number or whatever they're asking for of an unknown number. So distributive law, we can break up the numbers or the sums into more usable chunks. So 7 times 16 is the same as 7 times 10 plus 6. Doesn't matter. The numbers are the same. It's also the same as 7 plus 8 plus 8. 7 times 9 plus 7, so on and so forth. So we can, as long as we understand the basic rules of these three, I mean, this is like a few weeks worth I'm skimming through, but hopefully all of you have done that, and it's just a quick little rehash. So, the mul. Big, scary concept that even the toughest first year student, when they get to it, they often panic and overthink. And why we don't use kilograms as a measurement of the amount. So there's a concept we'll go through in a few weeks called stoichiometry. And in order to calculate what we need to in stoichiometry, we need to know what isn't there in the beginning. So if we have, so let's take nitrogen and hydrogen. The question says we have 84,000 grams of nitrogen. And we have 24,000 grams of hydrogen. Now, if we were to look at that on face value, and most of the time when you ask students, they will say there is more nitrogen. In this reaction that we will go through later on, there is more nitrogen, the hydrogen will run out first. And it's not true. And it perfectly illustrates why we don't use kilograms. We use the moles to represent how much of a certain element or something that we have. You can have moles of, I don't know, cat hair around, moles of eggs, it doesn't matter. So 84,000 grams of nitrogen. So I'll rehash this concept of the mole later on. But we have 84,000 grams. Now, we know that if we want to convert from one unit to another, I need to find the molar mass of nitrogen. And it would actually be N2, just to be picky. So, we would divide it. 1 grams per mole. So by doing this, we're cancelling out the grams, and we end up with 3,000 moles. Make sure you guys can see that. 3,000 moles. So we've cancelled out the grams, and we are working out the moles. So we now know we have 3,000 moles of nitrogen, or N2. So remember this number, 84,000 grams. I'll leave that there just because I'm writing it down. And we have 24,000 grams of H2, or hydrogen. So, and this is all about that conversion factor that we learned about in the beginning and putting it into practice. So, we have 24,000 grams. We need to divide it by molar mass of hydrogen. Sometimes these numbers vary depending on your textbooks and what your teacher might, the resources the teacher might give you. Always go by those, what numbers you're given. Grams per mole times 2, because it's H2. We then have, so we're cancelling out the grams because we're dividing and dividing. We get cancel out these two, and we're left with 11,900. So you can see why we don't use kilograms. Not in the majority of chemistry. We always have to convert using, this is unit 1, this is the conversion factor, and this is unit 2. Take it all the way back to that the second slide that we had. Unit 1, conversion factor. So grams per mole, which is the molar mass, 11,900 moles. We have 4 times as much hydrogen. from an atomic perspective than we did nitrogen. And now we know how to convert from grams to moles. Using that same equation, unit 1, conversion factor, unit 2. So, I think that's so. We've got specific heat capacity. This is going to be the homework / part of the tutorial questions because I'm not going to go through any on board. So C equals Q divide M times T. Sorry, delta T. So Q, so this is specific heat capacity, or the amount of energy required to lift the temperature of a substance by 1 degrees per gram. It's the official. So I'm going to leave that for you guys, and then I'll go through it in the first week, in the first sort of 5 minutes next week, maybe 10 minutes next week. I'll solve for Q, solve for M, and solve for delta T. Q being specific heat capacity of an object. Water is a common one, and it's 4.18. 4.184. M being the mass. Delta T being the change in temperature. And I'll go through that in the first 5, maybe 10 minutes next week. Don't worry about what it means, just rearrange form. It's a little bit more complex than the last one. So. Okay, I think I'll stop the first one there, 45 minutes. How do I stop the recording?